Welcome to this sailing theory tutorial. My name is Julian. In this video, we're going to be talking about tides. So what I'm planning on talking about today is the definition of tides and defining some related terms. I want to explain to you the physics behind what's causing tides. And we're going to talk about how you can find and interpret some local tidal information. So if we move on to our definitions section, the first thing that we have to define is the word tide itself. So what are tides? Well, tides are the rise and fall of the sea level caused by the gravitational pull of the sun and the moon. I'm going to highlight the moon here because the moon is actually the most important driving force for the tides. And the sun causes tides as well, but it's going to have a lesser effect than the moon. So most of us actually have some sort of experience with tides. Maybe we've been to the beach and we set up our lawn chair, or we built a sand castle right by the water's edge, and just a few hours later that sand castle has been completely destroyed by the waves. The waves didn't necessarily get bigger, maybe the tide just came in and the water level's higher. So we know that tides exist and they're a fact of life, we can't do anything about them. But this has two important implications for us as sailors. The first of which has to do with differences in water depth. So I want you to imagine that we have some water, and the water is concealing some underwater obstructions. Maybe they're rocks or something like that. If it's high tide, we can probably sail right over them, and we would never even know that they're there. Come back a few hours later though at low tide, and you have a whole other story. You might run aground and get stuck. Or, if you don't get stuck, you might damage your boat and take on water, and then eventually your boat might sink. Or, you might have some expensive repairs to deal with. So the second implication of tides that we want to focus on is that as the sea level goes up or down, water is going to flow in and out of coastal bays, rivers, inlets, etc. And this is going to cause tidal currents. So let's imagine a situation where we're in our boat and we're trying to sail towards shore. But the current situation with the tides is that the water level is dropping. And this is going to cause a current that's actually flowing offshore. So as we're trying to sail towards the shore and the water level is dropping, the water is going to be flowing away from the shore. And this is going to have an effect on our boat speed and the direction that we can sail through the water. So now that we've gone through all that, I want to split the rest of our definitions up into two categories that suit those two implications. So we'll start with the height of the tides. And our first term in that category is high tide. And this is simply when the water depth reaches its maximum for the current cycle. We're going to pair high tide with low tide, which is just the opposite, when the water depth reaches its minimum for the current cycle. And at this point, I'm going to tell you a little tide fact. In most locations on Earth, tide cycles are what we would call semi-diurnal. The word diurnal means daily, so semi-diurnal means that it happens twice per day. So I'm just going to draw a graph of the water depth for some imaginary day. And for this day, let's say that the first high tide that we're going to have is at midnight or 0 hours. What we would see then is approximately 6 hours later, we would experience some sort of low tide. And then 6 hours after that, we would expect the tide to be high again. 6 hours after that, it would be low. And then at 24 hours, we would actually be at midnight for the next day, and we would expect to see another high tide. And I'm going to tell you another tide fact now. So tides are not always going to be the same height in every cycle. Sometimes they're going to be higher and sometimes they're going to be lower. So with that fact, we're going to define a couple more terms. The first of which is spring tide. And a spring tide is when we have conditions that result in the greatest change of depth from low tide to high tide. What this means is that we'll have the highest high tides and the lowest low tides when we're experiencing a spring tide. The opposite of a spring tide is called a neap-tide, and this is when we have conditions that result in the smallest difference in depth from low tide to high tide. We might call these more moderate tides. If I were to draw that for you graphically, what I want to show you is the water level at high tide and the water level at low tide, and I want to compare a spring tide to a neap tide. What we'll see is if we draw an average water level line through this diagram, the variation from the average water level to the high tide and from the average water level to the low tide is bigger when we're experiencing a spring tide than when we're experiencing a neap tide. Now I want to give you one more tide fact. Spring tides and neap tides each occur twice per lunar month. So one lunar month is approximately 27.2 Earth days, and what that means is that about every 7 days we're going to have either a spring tide or a neap tide. So if today was spring tide, 7 days later I would experience a neap tide. And then 7 days after that, it would be a spring tide again. So spring tides have nothing to do with the spring season. They happen plenty of times in the year, not only when it's springtime. So now I think we can move on to our second category, which is the direction and the movement of water. And the first word that we're going to define is ebbing. So ebbing is what water does when it's flowing away from shore. So you could say that ebbing is referring to the direction of water flow away from shore. Colloquially, we might call this the tide going out. The counterpart to ebbing is flooding, and this is what happens when water is flowing towards shore. Colloquially, we would say that the tide is coming in. The last term that I'd like to define is something called slack tide, and slack tide is when the water is not moving at all. So this is going to occur briefly as the water changes direction at the high and low ends of the cycle. So that means it's going to happen at high tide and at low tide. And if you remember that high tide happens twice a day and low tide happens twice a day, that means that slack tide is going to happen 4 times per day. So now I guess we're going to discuss what causes the tides. And I know that we already said that the tides are caused by the gravitational pull of the sun and the moon. So it should come as no surprise that that's going to be my answer to this question. To talk about it in a little bit more depth, what I'd like to do is take a look at the orbit of the Earth around the sun and the orbit of the moon around the Earth. So most people know that the Earth goes around the sun once every 365 days. And many people also know that the moon goes around the Earth with respect to the sun once every 27.2 days. So if we take a look at that motion, we can notice a couple of things. One thing we're going to notice is that the position of the moon relative to the Earth is changing much faster than the position of the Earth relative to the sun. Another thing that we're going to notice is that the direction that the gravity force between the sun and the Earth and the direction of the gravity force between the moon and the Earth is going to be changing throughout the year and throughout the month, depending on the relative position of those bodies in space. Now what I'd like to do is reorganize the diagram a little bit. We're going to place the sun off to the left. We'll leave the Earth in line with the sun horizontally, and we can put the moon at some arbitrary position. We'll draw our force of gravity due to the moon and our force of gravity due to the sun along straight lines between the Earth and the sun and the Earth and the moon. And now, if we take those force of gravities for the sun and the moon, and we add the vector arrows tip to tail, what we can arrive at is a resultant total force of gravity vector. If we take that gravity vector with its magnitude and its direction, and we move it so that it points radially away from the Earth, what we're going to expect to see is that one of our regions that's going to experience high tide on the Earth is going to be right underneath that arrow. For now, I'd like you to just trust me that there's another region on the other side of the Earth that's also going to experience high tide. So the arrows that are underneath this light blue highlighted area are experiencing high tide. And let's say that the other two areas of the Earth that are not under this light blue are experiencing low tide. So we found a spot on the surface of the Earth that's experiencing high tide. Why is the tide going to come in and out or go up and down at that point? Well, there's another part of the motion of the Earth that we haven't talked about yet, and that's that the Earth actually rotates on its axis. So let's imagine that we're an observer at this red dot on the Earth's surface, and the Earth's going to rotate. What kind of tides are we going to experience at different times during the day? Well, as the observer on that red dot passes underneath the light blue region, I would expect them to be experiencing high tide. And as they leave the light blue region and pass through that unshaded region, I would expect them to see low tide until they approach the light blue region on the other side of the Earth, where they would start to experience high tide again. Finally, they'll experience low tide before coming back all the way around to the high tide region. Okay, so we understand how a point on Earth can rotate underneath the spot where gravity is acting between the sun and the moon, and that's going to give us high tide. But why do we have a second region of high tide on the backside of the Earth? Well, to explain that, I'm going to introduce to you the idea of differential forces. What we have set up here is an imaginary system with 1, 2, 3, 4, 5 piston cylinders. We're going to assume that the fluid down here can change shape, but it can't change volume. I'm going to propose to you a situation where we put loads on each of these cylinders. We can look at each of these masses and we can determine that the force of gravity is going to be proportional to the mass of each of the objects. So we would see 5 pounds of force on the 5-pound weight. We would see 8 pounds of force on the 8-pound weight, 1 pound of force on the 1-pound weights, and again 5 pounds on the 5-pound weight. So with gravity pulling each of these weights down, the question I'm going to ask is what direction is each weight going to move in? You might think initially that they're all going to go down, but that would be incorrect. Remember I said that the fluid in here can change shape, but it can't change volume. So if all of the cylinders moved down, we would be expecting that the volume of this fluid would be decreasing, and that's not possible. I'm going to propose to you a way to analyze the system though. So the first thing we're going to do is we're going to take all of these weights and add them up. So 5 plus 5 plus 1 plus 1 plus 8 is equal to 20 pounds. We could find an average force of gravity by dividing that 20 pounds by the 5 weights, and that's going to be 4 pounds. At each of the individual weights, we can subtract that average force from the force that we actually have acting on the weight. So 5 minus 4 gives us 1 pound of force. 8 minus 4 gives us 4 pounds of force. 1 minus 4 gives us minus 3 pounds of force. And 1 minus 4 minus 3. And again, 5 minus 4 gives us 1 pound of force. So what's going to happen if we release all of these from rest? Well, the 8-pound weight is going to move down, and it's going to move down as far as it can. The 5-pound weights are going to move down as well, but they're going to move down less far, about a quarter as far. And each of the 1 pound weights are going to move up about 3/4 as far as the 8 pound weight moved down. So let's get back to planet Earth and apply that concept again. Now, we've been talking a lot about the force of gravity, but we haven't really defined it yet. So gravity is defined by Newton's law of gravitation, which says that the force of gravity is equal to the gravitational constant times the mass of the first object times the mass of the second object divided by the radius that separates the two objects squared. In the case of the Earth and the Moon, we would be talking about the mass of the Earth, the mass of the Moon, and some distance that separates the Earth and the Moon. Now this diagram is not to scale, but the diameter of the Earth actually comes into play here when we're talking about the gravitational forces. So what we can see is that we actually have a couple of different radii in play here, depending on whether we're referring to the distance from the Moon to the close side of the Earth, or the distance from the Moon to the far side of the Earth. So we can take this information and we can use it to make a prediction about the relative size of the gravity vectors that are going to apply on either side of the Earth. So we might say that on the close side of the Earth, we have a pretty big gravity vector because we're pretty close between the Earth and the Moon. We'll call that FG1. We might say on the far side of the Earth, we have a larger radius, and a larger radius means that we're dividing this term by a larger number squared, which is going to make the force of gravity on the far side of the Earth less. We'll call that FG2. Now, to do our differential force analysis, we need to come up with some average force. The average force is not going to be the arithmetic average of both of these forces because we have this squared term in here. So to find the average force, what we're going to do is find the average force of gravity that would act on the Earth at the center of the Earth. We'll call the radius RC. And what we would expect to see is that this average force is going to be less than FG1, but it's going to be more than FG2. And we'll call that FG average. Now I'm going to copy the forces down below and we'll do our differential force analysis. Now to do our differential force analysis, we're going to subtract FG average from FG1 and from FG2. When we add vectors, we put them tip to tail and we measure the distance from the tail of the first vector to the tip of the second vector. To subtract vectors, we're going to place them tip to tip and we're going to measure the difference from the tail of the first vector to the tail of the second vector. And we'll call that one FD1. We'll repeat the process here for FG2 and F average, tip to tip. And we'll notice in this case that from the tail of the first vector to the tail of the second vector, we end up with FD2 pointing in the negative direction. Now what I want to do is take FD1 and FD2 and put them back up on the surface of the Earth. So what we've ended up with is our differential forces pointing in opposite directions on either side of the Earth. And this is where the idea of that double bulge comes in, where we end up with high tide on both the close side near the Moon and the far side far away from the Moon. So now I want to talk just a little bit more about spring and neap tides. And I want to present a couple of interesting positions that the Sun and the Moon can be in with respect to the Earth. So in this first position, we're going to say that the Sun and the Moon are in line with one another and in line with the Earth. And we're going to say that the force of gravity from the sun and that the force of gravity from the moon are both pulling in the same direction. If we add the force of gravity of the moon to the force of gravity from the sun, we can see that we end up with a pretty big vector. And that bigger vector there is going to cause a larger bulge on both sides of the Earth, which is going to be a spring tide. And when we have a spring tide, we know that we have a bigger difference between high tide and low tide. As the moon orbits the Earth, it'll eventually get to a point where it's pulling in a line that's perpendicular to the line that the sun makes with the Earth. In a case like this, we would have the force of gravity pulling perpendicular to the force of gravity from the sun. If we were to add these two together, we would end up with a resultant force that points off on an angle and is shorter than the absolute magnitude of those two vectors put together. So if we take that and we throw it over here, what we would expect to see is a smaller bulge on both sides of the Earth that doesn't quite point in line with the moon or with the sun. And we would call those Neap-Tides. And what we know about Neap-Tides is that the difference between high tide and low tide is closer together. We have more moderate tides. As the moon continues to orbit the Earth, eventually it ends up on the back side of the Earth. And in this case, we end up with a situation where the force of gravity for the moon and the force of gravity for the sun are pulling opposite to one another. To a certain degree, they're going to cancel one another out. But to a certain other degree, because of the differential forces that we've been talking about already, and the fact that we have two bulges, one on either side of the Earth, we're still going to expect to see spring tides in this condition. The last interesting position where we can find the moon is again perpendicular to the sun, but this time on the other side of the Earth. And in this situation, we end up with a very similar set of forces to what we had in our second interesting position. So if we add those two together, again what we're going to end up with is an angled force that causes a bulge on both sides of the Earth, but it's not going to be pointing straight towards either the sun or the moon. And we're going to call that Neap-Tide again. So this demonstrates how we end up with spring tides and Neap-Tides every 7 days, which is 2 times lunar month. So the last thing that I said that I was going to talk to you guys about was finding local tide information. The first place we can look for tide information is on a marine chart. And I'm going to show you some of the symbols that are going to exist on marine charts. You can see we have a symbol here for flood tidal stream with rate. What that means is the direction and the magnitude or the speed of the tidal current when the tide is coming in. We also have a symbol for the ebb tidal stream with rate. This is the same, but for when the tide is going out. Another important symbol that we're going to find on marine charts is the position of tabulated tidal stream data with designation. The other thing that we're going to want to look for on our marine chart is a place where there is a tide table published. You're going to be looking for names of harbors and things like that on the chart. The second place where we're going to look for tide information is in the tide tables themselves. This is where we get information on the water levels. In Canada, we can find the tide tables at www.waterlevel.gc.ca, and in the United States, we can find it on tidesandcurrent.noaa.gov. On both of these sites, we can get daily information for a specific locale. Unfortunately, in Canada, if you want the whole year's worth of data, you have to actually pay for it. I think it's free in the States. But at any rate, you can get daily information for free. So I wanted to show you an example of a tide table. I took this as a screenshot from the Canadian website, and it's the tide tables for today, which is April 10th, in Halifax, Nova Scotia. To show you the kind of information that you get, they give you a set of tables that'll show you a week's worth of tide information with the times of high and low tide twice per day. So to read this, at 4:24 local time, that's 4 in the morning, we would have a high tide that's 1.5 meters above chart datum. At 10:57 local time, which is 10:57 in the morning, we would have a low tide that is 0.6 meters above chart datum. At 17:21, we would have our second high tide, which again is going to be 1.5 meters above chart datum. And at 23:32, 11:30 in the evening, we would have our second low tide, and this low tide is a little bit higher than the first low tide at 0.7 meters above chart datum. So you could go through the whole week and find out when your high and your low tides are going to be. And sometimes, like on Wednesday, the second low tide or the second high tide is going to roll over into the next day. But most of the time, you're going to have 4 events per day. The other thing that they give you on the Canadian site is a table of predicted hourly heights. So again, they give it to you for a week. And as you read it across, if you were looking for Tuesday, you would see that at midnight, you're 0.9 meters above chart datum. At 1 in the morning, you're 1 meter above chart datum. At 2 in the morning, you're 1.2 meters above chart datum, and so on. And you can see that our water level here is growing until we get to around 6 in the morning, and then it starts to come down again until we get to around 11 in the morning. And then it'll be growing again until we get to around 17 hours, and then it'll be getting smaller again until we get to around midnight. And that's going to be low, high, low, high, low. So we can look this up for any day of the year. So this concludes my sailing theory tutorial on tides. In this video, we defined tides and a bunch of related terms. We talked about what causes tides and what causes variation in the size of tides. And at the very end, we talked a little bit about how to find local tide information. Be sure to check back again in my next video, where I'm going to try to put tide and current together and talk a little bit about how it affects your sailboat when you're sailing, and some strategy for racing in currents and tides. Thank you for watching.